Okay, so let's solve the same problem by the Newton's law of motion. In the last video, I solved this problem by using the principle of conservation of energy, and I promised that I'll be creating another video to solve it by the application of Newton's laws of motion. So, welcome to this video. In this video, I'll be solving the same problem using the Newton's law of motion. So, this was the last solution we achieved. Time period we found of this SHM system is 2 pi under root I by r square plus m divided by 4k. Okay, so now let's see approach 2 or solution 2 by applying Newton's laws of motion. So here we will not be talking anything about energy. We'll be just talking about the force, right? So just a recap on the last solution we did was this system will be initially equilibrium position and the natural elongation x naught of this system will be mg by 2k, right? So this is the same quantity we are going to reuse, right? So after the equilibrium, let's say you pull the system a little by distance of x. So what will happen? The tension, the two strings will not remain the same because there will be a rotational force. So that there will be a tension difference in the strings which will create the resultant torque, and that will make the pulley in the rotational force. So let's draw the free body diagram of the pulley once it is pulled by a distance of x, and then a pulley starts executing the simple harmonic motion, right? So let's say this one is there will be tension T1 and T2 in the string, right? And then there will be a mass force on the mass will be mg downward, right? And then there will be a rotational force also here. So what we'll be doing, we'll be equating, we'll be using the Newton's law of motion here. So for linear motion, let's apply the Newton's second law. What does Newton's second law say? It says that total force is equal to mass time acceleration, right? So total force is how much? Let's say this body is going downward with an acceleration a and velocity v at at time t. So total force mg downward minus t1 minus t2 upward, right, is equal to m times a. This is equation 1, right? And for rotational equilibrium, rotational motion, rotational motion is there will be torque. Let's assume that this is going down, right? If it is going down, it will move like this. So T2 will have more torque, right? T2 minus T1 times R. This is the rotational force equal to I alpha, where alpha rotational angular acceleration. Let's assume, or this you can also write I times A by R, equation number 2, right? So we consider linear motion, rotational motion of the pulley. Now consider the motion of the spring. So since spring is massless, what you, it's m times a will be 0, right? Because the mass is 0. So what you will get finally, just look at the spring, or let's draw the free body diagram of the spring. So this is spring. There will be some force, restoring force develop, which is k times x naught, and then this is T1 will be downward, restoring force will be upward. So since m times a is 0, so this will become x dash equal to T1. That's it. And what is x dash? X dash is the total elongation at the time t, right? So if pulley is going down by a distance x, we just discussed in the last video, there will be a total elongation 2x in the string. And natural elongation x naught, we already found x naught equal to mg by 2k. So total elongation at that time in the string or spring is x naught plus 2x, where x is the displacement of this pulley equal to T1, or k times x naught we already found in the equation 1. See here mg by, not mg by 2k. So I'll put this value here, mg by 2k plus 2x equal to T1, right? I am going to call this equation 3. Now let's see how many unknowns we have and how many equations we have. We have T1, T2, two unknown, and then X, three unknown, right? And we have three equations. Let's find out the value of T2 from 1 and 3. Okay, so from 1 and 3, mg minus T1 minus T2 equal to ma. Mg minus T1 is mg by 2k plus 2x minus T2 equal to ma, or this will become mg minus mg by 2 minus 2kx minus T2 equal to ma. This will become mg by 2 minus 2kx minus ma equal to T2. Okay, we got T1 and T2 both. We will put this value into equation 2. Put T1 and T2 in equation 2. mg by 2 minus 2kx minus ma. This is T2 minus T1 times R, right? T1 we already found, k times mg by 2k plus 2k, right? And all this times R equal to, sorry, all this equal to I times A by R. Okay, let's try to solve this. mg by 2 minus 2kx minus ma minus mg by 2 minus 2kx. times R equal to IA by R. So this mg by 2, this mg by 2 you can cut, and then it becomes minus 4kx minus ma equal to IA by R square, right? Or minus 4kx equal to m plus I by R square times A. This you can also write A equal to minus 4k by I by R square plus m, right, times x, or A equal to minus omega square x, where omega square equal to 4k by I by R square plus m. So what is this? This is the equation of simple harmonic motion, right? So using this, time period of the simple harmonic motion is 2 pi by omega, which is nothing but 2 pi times I by R square plus m divided by 4k. Now you see, this time period we found using the Newton's law of motion, and above in the last video we had found the time period again by principle of conservation of energy, right? They are exactly same. So as long as you apply the concept, right concept, your answers will always be same, irrespective of which theorem, which approach you are trying. Okay, hope this is making sense. Just go through it again once or twice, and then you should be able to understand it. If you feel any difficulty or see any difficulty at any stage, comment me, and then I will try to answer your question. Thank you, everyone. Bye bye.